Hello and welcome to our IRA seminar series. Today, live from the IRA office in Vienna. I have the great pleasure of introducing our distinguished speaker today, Dr. Roman Pflugfelder. Roman is a scientist at the Austrian Institute of Technology and a lecturer at TU Vienna. His research focuses on visual motion analysis, tracking, recognition, and visual learning applied to automated video surveillance. And Roman contributed with more than 60 papers and patents in the fields of camera calibration, object detection, object tracking, and event recognition. Roman is also a co-organizer of the Visual Object Tracking Challenges series in the past 8 years and a member of the steering committee of the AVSS conference. As a nice coincidental link to our traffic forecast competition, already more than 20 years ago, Roman used video surveillance for traffic monitoring. So very nice for me. And today, Roman will talk about the importance of motion perception in visual recognition and how this can open up a path to more robust and useful object detection compared to what you usually get with single image recognition. And so very much looking forward to the next hour.
Yes, thank you very much for this great introduction, and I'm very pleased to be here today. Thanks for this invitation. So I'm not a psychologist, and I'm also not a neuroscientist. I'm a computer vision expert. And so this work about the importance of motion perception in visual recognition is very much motivated also by applied research. I did together as a joint work with Axel Weissenfeld, Julian Piguaro, Georg Nebehey, and all my other students, Jonas Auer, Julian Wagner, Manuel Danne, and Michael Kammerhofer. And well, you would say, well, it's trivial actually to think about that motion perception is important in object recognition, and you're right. It's not new, but the literature is not so clear on that, how to do that actually, how to incorporate motion perception into visual recognition. And I try to shed some light today on this very important issue. Well, before I want to talk about the motion perception for object recognition, I would like to maybe introduce you to visual recognition. For those of you who come from maybe machine learning, pure machine learning, and not so familiar with computer vision. So visual recognition is one of the main themes, I would say, in computer vision, right? So basically, visual recognition is about, about a couple of tasks or components which are important in computer vision, very essential in computer vision. First of all, it's about, identification and also localization, I would say, of specific image regions which have specific properties, for example, coherence, so pixels which have the same intensity, for example, but might be also an image region which is the appearance or capturing the appearance of a specific object, like a person, for example. As you can see here in the illustration, these are, for example, interesting image regions which we call superpixels, for example, right? And there's a lot of work on that from the past, but still ongoing work on that. So object recognition or visual recognition is very much about identification and localization. A second part, I would say, of visual recognition is about then when we have found, current image regions, which might be from a specific object, we would like to categorize those image regions. We would like to understand and know what is it behind? Is it a chair? Is it a table? And this happens on different abstraction levels, right? So that can be very, very low level, I would say, for specific pixels, but it could be very high level when we talk, for example, about a chair. So a chair can be depicted or projected onto the image plane in various ways. And there are so many different kinds of chairs in the world. And for us humans, it's so easy. I show you a picture of a chair, and you tell me whether it's a chair. Might be that you never have seen this typical chair. So we have also this, we humans, we have this ability actually also to cope with unfamiliar objects. And that's also very important in visual recognition. Then there is, I think, a third important ingredient of visual recognition, which is then when we have image regions, so when we have identified those image regions, we have to, in a way, represent those, let's say by a descriptor. And we have, in a way, in this categorization process, one has to think about, something, how to describe classes of objects or categories of objects. Then we have to, in a way, match those two descriptors together. And that's, in a sense, a matching process, or it's actually the core recognition, one could say, right? And that's an inference process, right? Or in psychology, people say that's we try to relate things together, so relatability. So there are different kinds of wordings to the same procedure, I would say. Now, those different tasks I showed you before, they're very important for visual recognition, and they constitute the different areas in computer vision over the last 30 years, I would say. And they're still very, very active and ongoing and so on. So basically what you see here, what I show you here is, can you see this? No. Here. So basically when we talk about object recognition, computer vision, then on the one hand side, there is image classification as a whole area, or classical categorical image classification. So basically, I present you a picture, and there is a prominent object in the picture, for example, a chair, and the task is basically to infer that's a chair. So that's very prominent, and you all know that there was a big breakthrough in 2010, and then later on, to make this process really practical, and I don't have to, I think, emphasize that here. But it's still ongoing research field. And then there is another important research field, which is called object localization, I would say. So basically, for example, saliency detection. So there's a group of people working on saliency detection. So finding salient points in the image plane which have a specific property. So like as humans, we track with our eyes the environment, and at salient points we stop and we attend to that salient points and try to analyze what's behind. And that's basically a localization process. And that's a kind of a subfield or an area of object recognition. And when you combine those two things together, so the classification and localization, then we talk about object detection. And object detection is so popular today. I mean, with deep learning, for example, that was also kind of revolutionized, and we all know the work of the people at Facebook AI and YOLO and all these kind of detectors. They're all very important in different kinds of applications, where basically the task is to find, for example, a person or a car or a chair by a bounding box, and that's the localization part, and give it, a class label, for example, chair or person, right? So that's object detection. And based on object detection, there is another very important area, which is called object segmentation. So basically there, we're not happy with a bounding box alone, but we really want to segment pixel-wise, the whole image or image region, or part of the image. And there are two examples here, what I can show you here. Here, for example, that's a segmentation of this famous cameraman image. There, for example, people use, for example, clustering these pixels with k-means or so, which yield this segmentation, and that's very different to what I show you on the left-hand side, where you see a segmented image from the cityscapes dataset, where we call it, where this area is called kind of semantic segmentation. So you would also like to segment these different areas into different, types of objects like a road. So all the class labels here very important, right? So the roads and people and cars and things like this. So there's this, the core segmentation process is also combined with a classification at the pixel level. And we all know that when we combine multiple tasks, especially in modern methods coming from neural network theory, then we know that things getting more robust simply. And I think it's quite popular nowadays. So segmentation by simple k-means or fuzzy k-means, or what we have used all in the 90s, is kind of at the moment not so much emphasized. But I wanted to explain that here. Okay. So now, when we read this literature in visual recognition, either in object detection or in segmentation, all these kinds of different areas, and there are tons of papers every year, there are two persistent problems. And I think I call these persistent problems because I think these problems, they have been remaining for the last decade, I would say. And I show you here two examples. These are two images actually from two projects where I'm involved in at EIT. On the left side, you see there's a satellite image actually from the city of Khartoum, where you see the urban area and roads, and you see vehicles. And here the task is actually to detect those vehicles, right? So that was a task of our applied research project. I give you a satellite image. Please, could you detect all the cars in this satellite image? And on the right-hand side, this is another approach as a kind of the subject of another project where we consider classical object detection, and we would like to detect persons that's coming from the surveillance field in natural environments. So not in man-made environments, in natural environments. And in natural environments, you always have the problem of occlusion, or especially here, of the case of fragmented occlusion. So fragmented occlusion is something which is known in literature, in optical flow literature, but it's not so known, so well known, I would say, right? But that's very important here in this application. And what we recognize is that detection in the one case with these tiny vehicles is very hard and challenging. So that's a problem, even with the state of the art. And on the right-hand side, when you see this person behind the bush, behind this occluder, it seems that this is also very difficult with today's state of the art. And just to give you an example here, there is a paper from 2019, and they showed on 70 centimeters GSD images with the state-of-the-art deep learning object detection methods, an F1 score of 0.5. So basically, it's not usable, right? And the fragmented occlusion case I will show you later in the next slide is as challenging, right? And that's the reason also why we in this project came up with a challenge. I just want to make an advertisement here. So there is a new PATS challenge together with James Ferryman, who is the founder of the PATS challenges actually 20 years ago. And we have a challenge at AVSS conference at the moment running until the end of August. So we'd be happy if you would participate. Now, maybe to give you motivation. So basically, when you apply, the standard object detectors, we all know might be either faster RCN or YOLO, SSD, mask RCNN. They all not able to detect the person what you have seen before. So this nice bounding box is not coming from one of these detectors. That's actually made by hand, right? So, and I was thinking about this quite a lot of times in the last 2 years. So my observation in this case is that all these kind of state-of-the-art, very popular methods, they basically consider the case where they just consider a single image. Then they have their neural network model, and then the output basically are these bounding boxes, right? These locations and classification, of course, but they are kind of limited, by using a single image. So that's I would like now to go more into detail on this issue. But before I'm coming to that, and of course, so my hypothesis is that that's the limiting factor, that this single image processing will not allow us, for example, from this fragmented occlusion case, to detect a person reliably. But it's in a way assumption in the community, to rely on single images. So the question is, could we go beyond a single image? Could we use multiple images? I mean, that's not a new idea, right? So this is used, for example, in video segmentation. And people in the video segmentation field, they also not relying on a single image. They want to use a video to do segmentation. Or there is a community in computer vision, the tracking community. I'm also part of that tracking community for many years. So basically, we also consider not a single image. We consider also a sequence of images. And of course, there's optical flow community. So they are really kind of doing motion analysis, and based on that motion analysis, doing object recognition would be, a straightforward way to go. But in a way, all these methods, so when you read all these papers in these different fields, you have the impression, all these kind of models and papers, they rely all on 2 consecutive video frames. So basically, they're not considering a single, but they're considering 2 images, right? And the question is, if this is also limiting or not, and I can give you some empirical results later. Now, before I go further and show you maybe some results of our group, I would like maybe to bring you into another scientific discipline, human vision, maybe experimental psychology. I'm also not an expert there, but I'm very keen and interested in that. And so I started reading a little bit the literature. And what is interesting is that there is quite a broad literature on human motion perception. And there's also a quite broad literature on how we can use motion perception, or maybe ideas and concepts how we can use motion perception for visual recognition. And my feeling also is that this interdisciplinarity, or there are not so many links actually between those 2 fields. And so my intention actually today is actually to give you a little bit of an introduction of what people in human vision were thinking in the last years about problems like occlusion, for example. Well, basically human motion perception. So when you read the literature there, so that's basically about, light forms patterns on our retina changing with time. That's clear. And now the motion perception itself in the human is an unconscious inference, right? So it's totally unconscious. So the human seems not to be very much, attracted by human perception. So that's kind of something unconscious. Goes back actually to Hermann von Helmholtz, very famous German genius, I would say, and where he wrote a work, paper actually about the unbewusste Schluss in German. So and the psychologists, what do they say about motion perception? For what is it good for, right? That's interesting. So basically, human motion perception, or in humans, is very good for a lot of important things, especially for 3D shape reconstruction and 3D shape recognition, actually, right? And I'll show you an example in the next slides. For segmentation, as I said before, of, for example, camouflaged objects, the foreground has the same appearance, I would say, as the local background, right? distances, computing distances, computing time to collision. That's also known in computer vision, but that's also, of course, known in human vision. Or like computing directions, turning the head, all this motion is very essential, I would say, to steer all these processes. Actions. So action recognition. Of course, action happens in time, so motion perception is essential, I would say. And maybe what is interesting is there is mentioned kind of detecting something is moving and drawing attention to it. I think that sounds very simple for us and trivial, but for a machine that's not trivial at all. So first of all, detecting the something, the unfamiliar, that's very difficult actually, right? And then also to draw attention to it, how can we do that, So they're quite of interesting and a lot of challenging tasks, but very, very useful for us humans. For example, the 3D shape reconstruction. So here's an example of a three-dimensional object. And if I would ask you, to tell me, the three-dimensional form or look of this, it's very hard for you, I guess, to say that, with the single image. But now, when we see the video and the movement of this whole rigid object, I would say, suddenly it comes very, very clearly to your mind what you are seeing, right? Here is another example. That's also interesting because this is also a picture and a video we took in one of our projects at AIT. So as I said, I'm working in surveillance applications. So that's very typical. I would say you are at the border and you have a surveillance system there. And that's usually a thermal camera. So that's a thermal camera image. And it's a hot day. So that's the reason why it's so bright. There are trees, we are not in a man-made environment. We're usually in forests and, all much more challenging, I would say. And I ask you, can you recognize the object? And I think it's very difficult for you to recognize. What do you see there? But there is clearly something there. So it's not occluded, It has the same appearance as the background, right? So when I start the video, you immediately will recognize it, right? Here it is. So it's a person walking in this lawn. So the heat of the person, of the body, of the surface of the body is kind of equal to the background heat. So it's very, very essential, I think, and it's also very essential in nature. Because just think about all these strategies of animals to get to disappear from the world, to be camouflaged, that predators are not seeing, But when they start moving, of course, then they are endangered, and then the predator. So you can see this kind of concept of the importance of motion perception is very essential, I think, in evolution and also in nature, and that's clear. Now here is another example, and now coming back to the satellite image, and to this problem of detecting vehicles, right? So basically, this image captures a problem which is kind of burning under the nails of many urban planning people and so on. Can we have a technology, a sensor, with which we can count all the vehicles in a city just in a second, right? And I'm very thankful because this is not an image alone. That's a whole video from the orbit taken by a satellite from Planet. So thanks to Planet actually for providing me this data. You see here Khartoum again. So this is the capital of Sudan. It's not New York, so that has a reason. The reason is the project. So the people there were interested in Sudan and in Khartoum more than in other cities, and what you see here is that's raw data. It's not kind of pre-processed, it's just registered because there is ego motion included. So the satellite usually has its own ego motion. And so we try to register it to get rid of the ego motion of the satellite. And so my question is, can we not just think about, in this single image philosophy, I would say, or paradigm where people are currently working. I'm not saying everybody's working on that, but there are a lot of papers each year, they're working in this single image paradigm, I would say. When we would take one of these detectors and try to modify, and that's an applied research project, it's not a basic research project, and try to, adapt those, detectors to try to detect these very tiny vehicles, it's kind of hopeless, right? These are kind of 4 to 10 pixels, these cars, right? But and I think it's also difficult for you to see here these vehicles, right? But when I start the video, and hopefully you're now seeing it, maybe it might be that it's a bit difficult for you here to see that on this display, but you see here suddenly moving points, and because vehicles are moving, so we're not considering here static vehicles, we're just considering moving vehicles. And it seems for us, the task becomes easier, right? And so motion seems to be very important for this application, for this kind of detection, right? And I'll show you then some results later. So here is the last example of the series of examples. I just want to kind of motivate you that motion perception might be important for object recognition. That's also a photo taken from a border. So there are 2 trees, and you believe me, there is something behind these 2 trees, right? I just ask you, can you recognize what's behind those trees? So the people like in border surveillance call this through foliage detection. So that's actually, if somebody's out there who has a solution, please contact me, because there are so many border guards and people who are so keen and interested on solving this problem. Well, my observation is that taking just photos and trying to find those pixels who belong to a person, or for example, I think it's hopeless. But maybe if we have a sequence of images, then you might recognize that there is really an object behind those 2 trees. And it seems to be a person. And it's interesting because we even can say more about it. I see that the person has long hair. Might be a female. Could be. It could be also male, of course. I can see a sweater. I can see strips on a sweater. And it seems that the person has a backpack, something like this. So there is so much information in a video, which is not available in a single image. And it's a pity, actually, that people in object detection and object recognition are not using the whole information. Okay, so that just should motivate a little bit the presentation. Now, I would like to present you some results on those problems. As I said, that were all applied research projects. So basically, we took what we found in literature and tried to adapt it a little bit and to see, where we can go. And so our hypothesis here was, we don't want to take a single image. So we want to take at least 2 images, better, more images, so a sequence of images, a short video clip or something like this. The second assumption we made in this work is that we said, okay, we don't want to detect bounding boxes, for example. So in this detection process, people use usually bounding boxes. As you can imagine in this forestry scene, it's very hard even for a human to identify the correct bounding box, right? Because many parts are occluded. I mean, we see, okay, there is a person, but how can you really define a bounding box? So we gave this up and said, okay, we are happy when we just say, okay, position, right? So X, Y coordinate in the image, that's enough. So that led us to heat maps. So what you can see here on the bottom is basically a little bit the concept. So the input should be a sequence of images. The output should be something like a heat map. There's a little bit post-processing, which is necessary when you have multiple objects. But basically that's it. And then we would like to use some kind of neural network in between, right? And formulate the whole problem as a deep learning problem. That's what you would do in applied research nowadays, right? And try to collect data and do all the data engineering right. And so then was the question, what kind of networks could we consider? And so we considered basically three types of architecture. So the first architectural type was a classical convolutional neural network, which was reported in a CVPR paper in 2018, which was called FOVEANet. Was a paper by Mubarak Shaw's group, and we said, okay, let's work in this way that we have a multi-channel convolutional network. That means each channel represents one of these intensity video frames, right? We also use the UNet, so a more generative network, and we also use the UNet as a kind of a Siamese network, so not multi-channel, but there were two branches basically connected them together. Now I would like to show you some results. So basically this adapted FOVEANet, which is basically a classical convolutional neural network, we applied that to this cartoon video sequence. And so we trained it on training samples, so about 12,000 vehicles, which we didn't do, but a annotation company did for us. And then we had more than 3,000 test samples. And we used, classical L2 loss and Adam and so it was so in the heat map. I mean, we measured the loss, the Euclidean distance, and things like this, and so nothing special, right? And that's basically the result. So here, what you see here is this a single video frame, and you see these circles. They represent locations, which were found by the algorithm, which were peaks in this heat map, right? And it's interesting because, we can see here, for example, sorry. So there of course, there are these big roads. But for example, there is a car just in a suburb where not many cars are driving. But interestingly, over there is also a car which was not driving on a real road. It seems to be a sandy road or something like this. And I'll play the video to show a little bit more. So that what you could just imagine, what the result was, basically, yeah. And that's about 1.1 square kilometer of observation. What is interesting is that this is satellite video, which is a specific sensor modality. There is also another sensor modality now available, which can also capture more than 1.1 square kilometer, which can really go up to 100 square kilometers, or 10 square, at least 10 square kilometers, and but not with this high temporal resolution. So the temporal resolution here is about 50 hertz. There we have only 3 hertz, but I don't have any results at the moment on that. It's still a work in progress. Now, when we look a little bit closer, because that was really broad, I mean, it's not so easy to see, and look a little bit on quantitative results, we were really astonished, I have to say, about the results. So basically, this is just a junction, and it's just an enlargement. So what you see here, green are kind of true positives. So this is all manually annotated, right? Red, there are false negatives, and blue false positives. But very often, these false negatives, they are actually true positives. So it seems that the human annotator even had difficulties, because he had, just the raw data, and it was even difficult for him to do the annotation right? But of course, we did some analysis and computed the precision and recall, and then combined that, and we came up like with values of an F1 score of above actually 80%, so which is in this field actually very astonishing. I'll show you later some other results. So when we talk about the importance of motion and motion perception, we did some analysis, and this is the result. So what you see here is a recall precision curve of this FOVEA net on this cartoon video. And when we just feed it with a single image, we get this curve here, this blue one. And then when we use 3 consecutive video frames, we get much better results. And then for 5, it's still improving a little bit. But you see here, this big jump actually when we go from a single image to more than a single image. So that kind of proved also our observations for this one video. And then here, another video which we compared to, which is more well known in the literature because it's also publicly available. This Las Vegas video. So and so there of course there is some literature behind object vehicle detection in satellite videos, and there are all these kind of methods which are developed over the last years. And what you see on the bottom here is a FOVEA net, and then we adapted a little bit the FOVEA net and improved the overall results. So to, I think, quite interesting, quite practical numbers. So I don't say that can be done now for every kind of satellite video, because satellite videos, there are a lot of nuisances and kind of you have to pre-process them and so on. But that was quite astonishing for us. We published also these results, and there is also we're currently working on a journal article. So that was some work and results on this problem of tiny objects. Now I would like to show you some results on this occlusion problem. So what you see here is one of these images of a person walking behind these bushes. And for that we used a multi-channel UNet. And this is a typical, there are 4 sequences available now, and they're all part of this PATS challenge. What we did is we trained this network on unoccluded data. So we trained this network on the KTH data set, which is a data set quite old. It goes back to 2004. And so we choose that data because it has very simplistic background and a single person walking and showing some actions, right? It's the action recognition data set. But we wanted to have something simple and wanted to capture spatiotemporal information, and that was the reason to use that. And we trained it on unoccluded data and applied this network without any fine-tuning, nothing, to this very difficult and challenging video. And what you see here is the heat map output, actually. So when it gets more reddish, that's more like the position. And I'll just play the video. So what I have to say is, as the method is just trying to localize, we cut it out all the video frames which are showing an empty scene, right? So the algorithm at the moment is not able to distinguish between an empty scene and a person in a scene. And we were just interested in the localization accuracy, actually, and the precision. But that was also very astonishing for us that we can get such a result where classical object detection fails, actually. And I can show you that in the next slide. So we have a paper on that, actually, where we tried, these standard detectors like YOLO, fast RCNN, mask RCNN, on these different images coming from this through foliage detection problem, also on different levels. So on the right-hand side, you see a full visible person. And for that, of course, these standard, very popular detectors work very well. I mean, there is no problem with that for this kind of images. But then we try to capture people with more occlusion, partial occlusion, and then this kind of fragmented occlusion. And then these standard detectors failed quite quickly. Like that was class 1, fully visible, and that was a little bit occlusion, then more severe. And then finally, really hard occlusion, something like this, what you also have seen in this one video I showed you before. Well, there's a kind of total a breakdown, actually. So this is really a persistent problem in standard object detection. And it seems that motion is important, you know. So we did some experiment trying to find out a little bit more empirically. So what you see here is the number of video frames, so which you see here in the rows. That are the number of video frames considered. So a single image, and 3, and 5, 7, and so on and so forth. And that the temporal resolution. So we took every video frame or every second, and so we just try to reduce the temporal resolution here. And then we measured the true positives and computed the precision. As we said, we assumed, you know, that we don't have any, we don't consider at the moment, you know, like in a detector, the case where there's an empty scene. But it turned out, you know, that for seven video frames, when we feed 7 video frames into the network, then we get the best results with about 0.96 precision. Whereas and this is what we expected actually, for a single video frame, we were actually, this is not working at all. Right? So it seems that the number of video frames is important, and also that, for example, 3 and 5, of course, it's getting better, but that, for example, in this case, in this kind of example, just 7 were delivered the best results. So basically, most of the work in segmentation, for example, they consider 2 video frames, right? I'm not saying that, you know, that this is not possible, but it seems, you know, that more video frames seem to capture more information, and especially in this example, in this application. What is interesting was outcome of another experiment, and I just mentioned that we trained on an unoccluded data set, and we were able to get really good results on the occluded data, right? And so when you do that, just do that, you totally fail. But it was possible actually by reducing the colors, actually. By reducing the colors and even swapping colors, we were able to train the network on unoccluded data and apply it to occluded data. So what you see here on the bottom, this would be the original image, you know, with 256 intensities. And then here is a reduction by 2, by 2, by 2. I think these are 4 colors, you know. And when you look at the empirical results, and what you see here is the number of color bits. So these are 2 bits, so 4 colors, and 3 bits, 4 bits, and then also the temporal resolution. You see that for 2 bits, we get the best results. So the results break down quite quickly, actually, when we consider more colors. As you would expect, you know, when you would just take original images from KTH dataset to train it and then to apply it. And that was interesting. So one explanation to that is that it seems that, you know, we, in a way, when we reduce the colors, so reduce spatial information, that we try to force the network, you know, to learn more spatiotemporal features, you know, in the sequence of images. And that was interesting, and this is also information which is present in occluded and non-occluded case. So that was the reason, or seems to be the reason, that's an hypothesis from ourselves, why we were able to use the network learned on unoccluded data and applied it to occluded data. Of course, it's absolutely impossible to kind of collect a data set of occluded data, right? So if you would try to start collecting data of occluded images, there is such a big variety how occlusion can happen in the world. And that's also noticed in literature. So there is at the moment also no data set really available which shows occluded data for example, for the task of learning object detection or things like this. Okay, so just to recap, so what I have showed you now was that such very simple spatiotemporal networks, you were able kind of to localize vehicles which are about 4 to 10 pixels with an F1 score of 0.88 for this one example. And that's quite promising. Then we were able to localize persons behind these bushes, which is something really new, I would say, with a precision of 0.96, which is also very kind of promising. For this adapted FOVNet, we omitted the pooling because it turned out in our empirical results to kind of reduce actually accuracy, right? I will come back later on that. And that was really astonishing for us by reducing colors and maybe swapping colors. So disentangle or force learning actually not be able to learn much in the spatial domain, but in the temporal and spatiotemporal domain, we were able to train on unoccluded data and apply the network on occluded data and getting these results. So there is no theory behind that at the moment. So that's just empirical results. So from our applied research project, and it would be of course very interesting now to go deeper into that. And maybe so this is not. It's more a research plan, I would say. What I'm now presenting is, but the question is, what does such a network really learn, right? Why is it working, right? Why is it working for these persistent problems? And I would like maybe to now go back to the human vision research and show you some, especially for this occlusion problem, some interesting results from this discipline and try to use that theory actually to explain a little bit what might happen in the computer vision method actually. So first of all, this problem of occlusion in human motion perception is not new, right, in psychology. So it goes actually back to Hermann von Helmholtz to 1867, where he started his first slit experiments and tried to understand, how shape formation happens when occlusion happens actually. And also to show that how important it is motion for the visual perception of objects. So what you see here, for example, in this image, there's a specific type of object, there is a specific shape, and what I can say is that this object is moving, and it's shown at different time instances, different parts. And our question to you is, can you recognize the shape of the object? And it's impossible when you don't know the motion information, right? So now I show you the shape of the object, but there is also this velocity vector. So when you just imagine, that this kind of object is moving like from left to right, and now you can kind of collect all these pieces of information together, then you would be able, to kind of reconstruct and recognize the object. And that's really interesting work, which goes back really to Hermann von Helmholtz in this community. It is also known in this community that there are two causes of motion, right? So there is, on the one hand side, an observer can move. So you as a person move. And actually through a stationary environment, and that causes motion, right? As I move. Or on the other hand, that the object moves, right? And so I'm basically stationary. And in both cases, motion is in a way initiated, right? Of course, there is also a mix of both, right? So I can move and something else can move, like in this satellite case where there's this ego motion of the satellite and the motion of the vehicles. Now, what is interesting is, especially when it comes to occlusion and recognition, that there is an interesting theory which came out 2006 by Palmer, Kellman, and Shipley. And this theory, I just try to, explain it very broadly at this stage. And there are two components I would like now to explain. There is the concept or the component of persistence and position updating, which is shown by these two columns, A and B. So basically, when we talk about persistent, what does this mean? Well, this actually, this is the case when the occluder moves. So just imagine we have, for example, in this case, so people in psychology, they work with very simple objects. For example, here is a rod, right? And just imagine there is a display which is moving, which has two holes, right? So there we see this object by these holes. And when this display is moving, then you see at time t1, you see the lower part of the rod. And at the time t2, you see the upper part of the rod, right? And now, what does persistence mean? And that goes back actually to a psychologist called Sperling, and that was one of his experiments. And then to another psychologist, Neisser, 1967, who coined this term visual icon. So we as humans, it seems we are able to, in a way, see something, a fragment of an object, and then to memorize it for a short time. And this is actually what is called persistent. So we, in a way, in our mind, these parts become persistent for some time. And that allows us basically to see the object as a whole, when you see the parts at different time instances, and then you can combine that, and that's a recognition process. But persistence is a very essential component of that. On the other hand, there is as I said before, there is also the case when the rod moves. So when it's occluded, this display stays stationary. So when the rod moves, then you also see this part at different time instances, but at different locations now, because the rod is moving, right? So the persistence alone is not enough, So you need some kind of component that is able to track or to, update, that's called positioning updating. So kind of updating the position of these different fragments you're seeing to bring it to align, these different fragments into a whole picture. And this is called also a visual icon, right? In this case, a dynamic visual icon that was also named by Palmer, Kellman, and Shipley. To make the recognition process possible. On these two components, they formulated a theory of spatiotemporal relatability. And what you see here in this illustration, there are three kind of concepts. So basically, this spatiotemporal relatability is kind of founded on something like a dynamic visible region representation. So basically, when some fragment like this part of the rod becomes visible, then we as humans are able to capture the shape of just of this visible part, right? And for that, we need a representation, of course. And of course, we can also, to a certain extent, we all know there are problems with that, but in a way, we can, estimate some part of the motion, how it's moving. But there is a aperture problem, so it's challenging, right? And it's not possible in many cases. But at least we get some sense of the motion. And the positioning updating is also represented. They call this a dynamic visual icon. So basically, we humans, we are able to, in a way, track, in the occluded part, we can track this before visible and non-occluded part of the rod further, right? to the next stage, to the next time instant, T2, right? And then when we see the upper part of the rod, we can combine both. And that's they call that spatiotemporal contour interpolation, or it's actually this recognition, right? This matching, I mentioned before, this inference process. And by that, we recognize, okay, that's a rod. I have here maybe a better example. What you see here, these two columns, there on the left, you see the video frames. So you see here, there's a window, somebody's looking out of the window, there's a tree, and there's a road, and there is something moving from left to the right. From A, B, C, D, you see this motion, and it's actually a fire truck. What you see on the right-hand side is basically these fragments, these little slits, actually, what you have seen before, what you see on the left-hand side, which becomes visible at different time instances. So here we see a little bit, of the fire truck, and then it moves further, and then we see here a little bit, and this moves further, we see more, and in D it moves more to the right, and we see a little bit here. And by this theory, by these concepts I've just explained before, we are able to kind of align in a spatial canvas, I would say, all these different fragments by this persistence and by this positional updating, align it together, and that would form this image here. And for us, and this is now very easy for us to recognize this is a fire truck. And I think it's a very interesting theory how this object recognition under occlusion could work, right? And I would like also to mention that like recognition of totally kind of unoccluded objects as it is seen here is much simpler, and it's today with the methods we have, is actually works quite well, I have to say. What's always the problem are these nuisances like occlusion and so on. Okay, I just read the theory, and I was thinking about about the spatiotemporal network and why it works so well, and try to understand if we could in a way apply those theoretical concepts to what we showed empirically. And so I was thinking about persistence and what does it mean actually, persistence in our case. And so so basically, we as I said, we don't have a single image. We have a video sequence, as you see it here, either coming from, let's say, this camera, which is observing a person behind a bush walking, or let's say in this tiny object detection case where we have a satellite moving over a city or so and taking images. So basically, we see the person at different time instances, and basically persistence, what does it mean? It means that we keep different fragments, different parts of an object present in our mind. That's basically by construction done by the video itself, by the data. So the data kind of hold the whole information persistent for us. So in a way, persistence is in a way realized by the data itself. So like, for example, video aggregates color, shape, the kind of motion information, size, orientation, all these kinds of things. Okay. Now, what about position updating? Might it be that this spatiotemporal network we use, that it does do in a way such kind of position updating as the psychologists think how the human vision and occlusion, or the human recognition and occlusion works? I was thinking a little bit about that, and so this is just ideas and hypotheses. But basically, when we consider a convolutional neural network, okay, we have as an input, we have these images, right, as channels. And now what happens is that we have convolutional layers. So those convolutional layers, they compute feature maps from one layer to the next. So basically, at the low layers, very fine details, right? The receptive fields are quite small, a couple of pixels and so on. But when you go up in the network layer hierarchy, or you increase the depth, of course, these receptive fields become larger and larger. So my intuition was about, that these lower layers, they're basically like these little slits, right? So they capture, they kind of represent, these little fragments which we see through these slits, right? And now when we go up the hierarchy, then these convolutional filters, they are able to, in a way, correlate different fragments, and in a way they can solve this correspondence problem. So they can produce a response for certain fragments at certain positions in different video frames, actually. And by that, solving actually this position updating problem. So they can relate, different, and I'm talking about compositional features. So going up actually in the hierarchy. And of course, pooling would also disturb that and would not be good actually to do max pooling. And that's what we actually, at least empirically, what we observed. But when you use pooling, that is disturbing this process. And so what you see in the bottom actually is what might happen is that the network tries, to solve this problem of aligning those images, right? What happens actually in this theory of, computing this positional updating, right? For the recognition itself. So basically, when you go through the convolutional network, you compute features, you compute compositional features. These features are not only spatial, they're also spatiotemporal. So we capture motion information. And when you go up, the receptive field grows, and those filters are able to kind of correlate different features from different parts together, and in a way could come up with feature maps in higher layers, which represent something like, positional information where an object could be, right? And now the last step would be, to, in a way, relate all those features in the feature maps of this last layer. And to relate them, what could this mean? So this last step in the recognition. And I was thinking about this, and I looked into this different network architectures, and all these network architectures, what we used in our applied research, they all had as a last layer a one-by-one convolution. Okay, and I was thinking, okay, that would be natural actually to think about this one-by-one convolution, about this operation now to relate all these neurons of all these feature maps to a single, for example, heat map. When we talk about position, to find a position, find a heat map, to relate all them. And when you look here, that would be, for example, so that would be, there would be these feature maps of the last layer. So that would be some kind of neuron MN. That would be some, we take out a single pixel in the feature map, and then we go through all those neurons which are related now, related by the spatial outline of the feature maps themselves as matrices. And then in a way, what we do is we sum up all that and of course multiply that by coefficient. That's what a one-by-one convolution basically does, right? And I was thinking, okay, for the occlusion case, there is some literature on so-called integral images. So basically, what you see here on the left-hand side, that's an original image. And just now, I have not only a single image, but let's say I have multiple images and aligned images, as my intuition would be what the convolutional layers in the lower layers are doing, actually. When I not just do averaging, and basically that would be the averaging operation, that would be something like a mean pooling, which is also could be realized by a one-by-one convolution, more general convolution, then you get this result, basically. And just, I don't know if this can be seen, but when you apply this one-by-one convolution, or basically mean pooling, to these aligned images, which you could realize as let's say, feature maps of the last layer, then suddenly all these kind of occlusion are kind of averaged out, like you could imagine, like noise, right? That's basically actually the idea of this integral image approach, which is also was discovered by Kormi, Schedel, Bimber from 2019. And you see here, suddenly there, the outline of the person. So here you can really see now nicely the person, and you could imagine that now a recognition would do much easier, right, on this. Of course, these are all kind of observations. I would like to maybe show you another part of work we have done a couple of years ago, which also in a way relate to this theory of spatiotemporal relatability. And I would just like to mention that because spatiotemporal networks are one kind of method. Of course, there's tracking as a whole field, I would say, in computer vision, which is also considering motion, right? And I would like maybe to just introduce that a little bit. So basically, today, what you see in the tracking community, of course, tracking is a motion analysis method, basically. So tracking tries also to help you analyzing the motion in a video. But basically today, tracking is more like an object recognition. It's actually basically, it's basically an instance-based object detector. So basically, how the tracking community today sees tracking is in this tracking by detection paradigm. So basically, we have a patch of an object given, let's say, and then now we have a video sequence, and we actually know in the first video frame where the, for example, this object is located, and then from there we try, to track through the video, right, the object, the person or the car or whatever, and so basically this is and the current state of the art. There are actually two approaches. There are people using Siamese networks for this task, or correlation filters, and they all work as shown in this image here. Basically, so they kind of try to. We have a representation of the object and try to match such a patch representation. Usually, the people use bounding boxes, right? And we try to match, let's say, a rectangular patch with a search image region. It could be usually it's not the whole image, right? It's a part of the image because we start in the appropriate location. But there is no motion information included or something like this. It's really, there is of course learning. There's adaptation sometimes, so this patch is adapted, over time. But basically, there is no motion information included nowadays in the state of the art, I would say, right? I would like to draw the attention also to this occlusion problem. So basically, people in the last 20 years or so in object tracking, they consider different kinds of, I would say, state descriptors, right? So there is an appearance descriptor which captures the appearance. This is something like inside of the bounding box, There is a small image patch, and that's then represented, let's say, by features, right? Today, everybody uses CNNs, to capture these, features, right? But basically, where I want to go is that they all assume a bounding box, for example. But this is not the only way how we can represent the object outline and also motion, because motion would be something like the first derivative of this, right? So how the bounding box changes over time. For example, we did that also in our VOD challenge, and some people started working then on that, on, let's say, rotated bounding boxes. So we allowed the bounding box also to rotate. So we had another parameter, a motion parameter to estimate, right? But when you look into the literature and you just try to enumerate what's possible, then you come up something with this. So on the top left, that would be, you would describe the object with a key point, a position, and maybe a velocity. That looks very similar to what we have seen before in the psychology literature. So very simple, but people worked on that. I don't know, in the 80s, 90s, people worked on Kalman filtering, or in 2000, I also worked on that, right? Then you could consider multiple points. You could consider bounding box, which is, as I said, popular. What is now popular in the tracking community is actually to really consider a pixel-wise segmentation. So really people try now to describe the object by the contour, basically, and to actually do a segmentation, right? Of course, there are many, many more options in between, you know, but I'm not emphasizing this too much. What I want to say and where I want to lead you is basically that when we consider this occlusion problem, it doesn't mind actually what kind of, you know, kind of state descriptor you're using. Just imagine we would use the bounding box, which is the standard today in tracking. So all kind of popular trackers, they use the bounding box, right? Just imagine, you know, this video again, you know, with the bushes and with the person behind the bush. Would you choose a bounding box to describe the object and try to estimate really very, very precisely, you know, position and width and height of the bounding box when so many parts are occluded? I think that's very error prone, I guess, right? And difficult. The same maybe with segmentation. Much easier maybe when you just have one point, as I have shown before with the heat map, right? And we are not considering at the moment the velocity vector, right? So this is not considered there. Maybe even more robust would be considering a couple of points, you know, as in the psychology experiments where all these fragments, they pop up at different positions. So when we could capture all that and presently maintain that, that would be even more robust, you know. And so this work we did 2014 and 15 was towards this direction, you know. That was work on, and we named this tracker consensus-based matching and tracking, and it's in a way aligned with this spatiotemporal relatability theory from psychology. And what you see here, so basically this tracker, the state is basically defined on all these kind of green key points. So it's a kind of a redundancy in there to be more robust. The blue box, this bounding box, was mainly for evaluation purposes. So we had to compute that to be able to, you know, compare to the benchmarks. But it was not, that was just a side product. It was not the state vector we updated, right? And so when that was basically the result of this tracker. So basically, when it comes to occlusion and so on, that was quite robust, you know, and in a way much more robust when you would just consider a bounding box. Don't be misled by these charms of the bounding box, because they are not. They're just a side product, as I said. Okay. Maybe just a little bit. I just want to maybe just relate a little bit what we did at that time to this spatiotemporal relatability theory. So basically, the persistence there in this method was given actually by this exemplar right at the beginning. So we had an exemplar right at the beginning we would like to track. This is actually the normal case in tracking. And now we described this patch actually, not by CNN features, but we described it by a number of key points and with smaller descriptors. At that time, it was very keen using BRISC and all these kind of binary descriptors. Today, maybe one would use CNN features or some kind of other neural network-based descriptors. So basically, we captured, you know, this visual icon right at the beginning. And then this position and updating was done basically by tracking each of these key points individually, I would say. And the tracking, I don't want to maybe to go too much into detail here. So basically, the state was a correspondence between the very first image patch we had, all these key points, to a current appearance of the object in the current video frame at time t. You know, there are the key points here visible, and then we try to relate those, and these are these correspondences which are these MIs, and there are of course not a single correspondence, there are multiple correspondences. So that was basically our state, and we tried to keep this state updated, right? And we did that basically by very simple sparse optical flow. So we tracked these key points simply. That gave us kind of this adaptivity, I would say, you know. Of course, that's very often error prone, you know. Sometimes there's the occlusion and then, you know, you lose this correspondence. I'm just going over that. But for that, as a kind of as an alternative, we use descriptor matching. So basically, we matched descriptors from the very first image patch from the key points to the actual key points we received in the video frame at time t. So that also formed correspondences. That's very conservative because okay, we have a single positive, I would say, you know, and that introduced correct correspondences over time again. So that was the solution to this. I would say to this stability plasticity dilemma, I would say, right? So we had this positional updating actually implemented by this tracking component, I would say. And then we aggregated those correspondences. Correspondences coming from the optical flow and correspondences coming from the descriptor matching, you know, that introduced again correspondences. And now when it comes to this relatability, so basically the relatability was in a way realized by a consensus model, which is actually kind of an idea going back to generalized Huff transform. So basically in this first patch, we defined some consensus point or some kind of point that could be anywhere in the image, and then computed velocity or relatability vectors. Where is it? Those relatability vectors, and that captured these the spatial statistics actually of this image patch, right? So that's very typical. I mean, there was an assumption behind that basically, you know, it's a rigid object, you know, and that these statistics does not change too much over time. But that was basically the information we used then to relate, you know, to relate those correspondences. And I just would like to show you what this means. So basically, first to compute similarity and rotation, so kind of this transformation, which the object undergoes. So when you have, for example, here the key points, and then those consensus vectors, they look anywhere, and you would like now to compute the rotation to this original first image patch. So you turn, for example, you rotate that, and then it kind of ends in a consensus again. Then you have found basically, you know, for example, rotation or similarity, you know, to make it larger or smaller. And so on the one hand side, that was with this consensus model, we were able to estimate this motion information. And then of course, we were also able to detect errors because we did some agglomerative clustering based on these consensus models, on these vectors. And of course, there were always wrong correspondences, and by that we were able to identify those, right? And remove those outliers. But with this descriptor matching, we introduced again, you know, correct correspondences again over time. And so in a way, at that time, and that just came up, you know, in the last couple of months, actually, we also kind of, you know, did some work towards, you know, a little bit in alignment with this spatiotemporal relatability theory from psychology. That was interesting also to me. Well, now I would like to conclude. So what I've shown you is that motion perception is important for object recognition, at least for the human vision researchers. And I think it should be also important for us, computer vision researchers. There are really persistent problems over many decades, I would say, still big problems for example, in tracking. We have now a challenge at ICCV where occlusion is the persistent problem, I would say, in the challenge. We see this. So the most failures of all the trackers come from occlusion. And it seems that occlusion can be handled by kind of taking motion into consideration and developing the right methodology and methods and models to combine motion perception and object recognition to get better, more robust object recognition methods. Maybe one way to better understand this problem is maybe to look into psychology literature and to see what people there are doing and what ideas they have. And I just found this spatiotemporal relatability theory from Palmer, Kalman, and Shipley. And I found this very inspiring. And I tried to introduce you into that. And what I want to say is that the tracking basically today is motion analysis and object recognition. So basically, today people actually work on instance-based object detection when we talk about tracking, right? And that a key, I think, a key idea also is to introduce redundancy in the data. So either in this consensus model, as I showed you, introduce redundancy by multiple key points we have, because when some of them are occluded, we still have others which can help staying robust, I would say, to reliably localize the object. Or I would say in the temporal domain, as we have seen, for example, with these tiny objects, where we introduce redundancy by having multiple video frames where the same object is repeatedly visible. Although it's tiny, it's 4 to 10 pixels, by this redundancy, we can develop more robust methods. So this concludes my talk. Thank you very much.
Okay, excellent. Thank you very much, Roman. I think we have already one first question from our chat, from Rahul Siripurapu. So perhaps one way to explain why reducing colors helps in occluded detection is that removing some color information naturally incorporates the prior that objects tend to have a uniform color. So reducing the image color is basically going in favor of more constant colored objects.
Yeah, I mean, by reducing the color, basically we do some kind of segmentation. So basically, more and more, the object we would like actually to localize stays visible, and all the other information, like detailed information, the background, is kind of, is reduced or is eliminated, basically. And that definitely, I guess, helps in improving on the localization. But I think also what we recognized also in our experiments is when you train on let's say on the full color images, then there are always kind of feature combinations or even pixels. So the learning process is so discriminative that it is able, to really find very, very, very particular, for this just one video or so, very particular spatial bits and pieces, to explain, for example, some kind of localization. It's not really generalizing, and I think that helps in better generalizing. But of course, this is just one observation in one video and in one single project. So much more work has to be done on that,
Yeah. So just from my from my own experience working with pictures and stuff like on Photoshop, sometimes it can also be treachery, right? Because you can have this fake classification, because for whatever exposure or other camera problems, you suddenly might have a cut in your normally nicely classified segments, and suddenly it doesn't work anymore.
Yeah.
So that might.
I mean, you're totally right, and I think also the network really does not learn a concept of, let's say, a person or something like this. Basically, I think what it learns is really because we have also experiments, especially with the tiny objects, and applying these multi-channel spatiotemporal to the tiny objects, that it was also able to detect, let's say, for example, a truck or even a train, so parts of a train. So it does not really, learn a concept, let's say, of this human, but in a way, it learns this movement, let's say, in a spatiotemporal domain. Like what it really can learn is let's say, these trajectories, I would say, how these objects are moving, and so on. And when there is a video, a test video, maybe a different object, but moves in the same way, maybe at the same speed, at the same position, in the same direction, then it would be recognized or located as well. So I think it's not really learning a concept really of the object itself. Yeah.
Thank you. The other thing that you have shown was when you train with 1, 2, 3, 4, or 5 frames, that it becomes better until 3 frames, and then the quality, the precision drops again. So that is kind of in contradiction what you just said, I think, or as I interpret. You said it learns to understand this trajectory, but then it should become better when you use more frames, right? I was surprised why it gets worse. I think 4 and 5 frames were worse than 2 frames.
So for example, so here it's really, precision is quite bad, getting better, and then with 7 we get this result, and then with 11 we get the same result again. So what we did not do more experiments with longer video sequences, but what we recognized here was that there is a convergence, actually, right? It's not getting better, it's kind of converging, right? And the reason is also because this kind of in the setup was that we wanted to compute the heat map for the center video frame. So we have, let's say, that's the reason why there are odd numbers, right? So for 7 video frames, we computed the location, the heat map of the fourth one, actually. And so when you add left and right, in time, additional video frames, okay, you introduce more information, but it becomes more and more decorrelated, I think, from the, so, because in principle, motion can be arbitrary the more you go into the past or future for a specific time instant, And that might be also maybe an explanation why, when you're adding more and more video frames, why this has to converge to a certain sense, because it might be even decrease a little bit because, this is totally decorrelated. So locally there is some correlation, but not over the whole, over long video sequence, I guess.
I have also a follow-up question to that one. So is there any relation to the speed of the object or of the movement? Because a human moves at a certain speed, a car would have a much higher speed or something like that. So especially in that table.
Yeah, we did some experiments on that, and there is, of course, an influence. So it's not invariant to speed or so. So basically, and that would also explain that it might be that this network learns some kind of concept of trajectories in the space-time, right? That, of course, when there's double speed, then the trajectory would be just steeper in this image space, and of course we would need examples to learn that. So it's not invariant to that, right?
Thank you very much. Very, very nice talk. I liked your one-by-one convolutions very much. Can I understand it correctly? The image you showed, is it just the application of a one-by-one convolution on basically a sequence of frames? And you mentioned that normally they were sort of applied in higher layers. Did you then shift them further down? Because it could be that close to the input, you do a one-by-one convolution, this nice averaging out, and then let the neural network take it up from there? Or what was the architecture?
Mm-hmm. Yeah. My thinking was, okay, there are these architectures, and all these architectures to show this one-by-one convolution. And how can I relate now this one-by-one? How could I explain, the cause of this one-by-one convolution in this idea, in this concept of the theory, what the psychologist actually. And so in this concept of the psychologist, this one convolution has the function, or the concept is to relate, you know, all these feature maps after the last convolution layer, to in a way to fuse all this information together to produce a single heat map. And for this tiny object detection, maybe the idea would be that these feature maps of this last layer, these neurons, they produce kind of responses where the network thinks, okay, there is a car, but of course it's very unreliable because it's just very small, 4 to 10 pixels. But by considering multiple feature maps, and by this aggregation process, we could, you know, kind of increase this evidence. So that's kind of the idea of that, right? So this is just, for me, try to understand from a causal point of view what is network learns. I don't have any proof at the moment, so.
No, I like the heuristics very much,
yeah.
really a lot. But actually, with that heuristic, you could also argue, why not stick it lower down if your image model, you know, lower down closer to the input. So it forces actually an averaging, or it forces it to learn some weights, which might be an averaging, lower down, so that the upper layers.
My explanation to that is what I kind of understood under this concept of position and updating. So basically, that would be the input layer, right? These are really these images, right? So then just imagine we have the first convolutional layer. So the first convolution layer, these are really filters like 3 by 3. So they go over those images, right? In a spatiotemporal as a domain. So they are kind of 3D convolutions, I would say. Well, they are 2D convolutions in our experiments, but they could be interpreted as a 3D convolution, you know? And so they produce, in the first feature map, they would produce spatiotemporal features, but in a very tiny local neighborhood of pixels, right? So let's say now, just imagine that would be occluded, just like here and so on. But in the spatiotemporal domain, it's a bit difficult to understand, you know. It's not just in the image, you know. And that would kind of create the first kind of feature maps. And then we would again apply a convolutional layer. So this would be also 3 by 3 kernel filter, or 3 by 3 kernel filters, give also a number of feature maps. But this is now compositional. So this is based on the first output, right? So that increases a little bit the receptive field in this 3-dimensional domain, not just in the image, right? So that would relate a little bit more, right, in the vicinity, because this object can move from the right to the left. So there is, in the first layers, no possibility for the network to learn some relationships between the left part and the right part. And that's and so we need more convolutions, a deeper network, to be able, that convolutional layers, let's say in the 5th layer, for example, because of the receptive field, they're able, because of this compositional architecture, to in a way, by the convolution, relate, of course in a linear way, let's say pixels in this area, in the spatiotemporal domain, so spatiotemporal features actually, with this, right? And my intuition is that these correlations, these filter responses, they are very much driven by this idea of correspondence. So those higher, the lower level convolutional filters, to try to find discriminative features, and features which are kind of, in a way, describe these fragments which can be seen of the person, let's say. Or in this case, we see the whole person, actually, right? But that's okay, because when things become occluded, still they are available, right? Some features are kind of occluded, but still some features are available, and that might be also explanation why this works, why we can train on unoccluded data and apply it then on occluded data, right? And this is what I wanted to show here with this. So basically these convolutional filters try to, you could see it also from the other side, try to move those frames in a way that here all these people kind of are overlaid. The same person is overlaid at the right position of this middle frame, right? And then and so the feature maps after this last convolutional filter, they are in a way represent, you know, these transformed right input images where the person is overlaid, and then this relatability, this one-by-one convolution, just, you know, aggregates that information. And produces a heat map output at exactly that position. You know, I don't have had a deeper look into that, right? That's just an intuition, you know, what I wanted to present here. Or in other words, it could also give ideas, because I did some experiment with the original input layer images. So I transformed them, brought them into alignment, and just computed the mean image, right? And that what you see on the right-hand side is the mean image. You know? So if you would have a procedure, not in a neural network, but if you would have a procedure aligning those images, basically finding these correspondences, bringing them into alignment, and computing a mean image, it's called an integral image. And this is not new, right? This is something which was published. Then you could get rid of this occlusion. That was presented in a little bit in another setting, where they call that aerial optical sectioning. So basically, the application was there was a drone, and the drone took a couple of images, and so they could kind of simulate a synthetic aperture. So they had a light field, and then they calibrated. They had a calibration information, and they were able, you know, to bring all these pictures, these different pictures, into alignment by this known calibration. And then they just simply did this averaging and came up with this nice solution. And basically, that was a very interesting example to how you can do through foliage detection, because I said I have been working in this project of through foliage detection, and that's a very feasible approach now. And there's actually colleagues from JK Linz, actually. Oliver is from JK Linz, and he has now even a prototype available, and they're just really now working on a product, I think, together maybe with a company or so. I'm not following this anymore, but that was inspiring for me to also think about, you know, how this could explain maybe why our spatiotemporal network also was able to localize a person in the occluded video.
Hi. I have a couple of questions related with the data on these experiments. So first is, was the annotation made manually, or were those are there any data sets publicly available to do that? Because there are different cases. For instance, the very tiny objects are circles. Did you annotate them manually, or was or this was publicly available? In the other cases, for instance, in the occlusion cases, in the case when you use the dots to represent or to track the object, were those added manually or prior training? I mean.
Mm-hmm. So yeah, I can answer this question. On this left-hand side with the satellite video, we did annotation. We annotated by annotation company. So we annotated this manually. So people annotated really all the vehicles in certain areas of interest. So not in the whole, not on the whole in the whole video, because it's far too large. But for some areas of interest, we did annotation. That's not publicly available, but I hope that we can make it publicly available. And that depends more or less on the company, on Planet, if they allow this. But I'm very I'm kind of looking forward that this can happen. Okay. And in the other case with the occlusion, We also did that annotation by hand, also with an annotation company, where we had two approaches. One was really drawing bounding boxes, where we then found out that this is very difficult. But for some cases, for example, in this case, it works, right? Because there is fragmented occlusion, but still you see frontier points like on the head and feet. So it's still possible to draw a bounding box, I would say. But there are also cases where you see just fragments, as you have seen. And for that, the annotators, there we had a totally kind of new procedure, how to annotate that. And basically that was still is an ongoing work to annotate that with kind of key points, right? With a set of points. So trying to, annotate appearances where the annotator really sees the object, where there is no occlusion and draws a pointer. So basically this appearance was kind of sampled, right, by manual defining points. And this is at the moment partially available publicly. As I said, there is this PATS challenge, so you can download data there now. We're looking forward that we might also release a little bit more data this year. But when you're interested, just contact me and we can talk. When you're interested in such kind of data, there should be no problem to share that, because we can share this data. So we have the allowance to share this data with the public, or at least with the research community.
Great, thanks. I have another question. So did I understood correctly, in all the experiments, the color dimension was dropped in favor of the temporal steps to use them as the third channel in the input to the network? I mean, so normally the tensor that you input into the network has the three channel. The third channel is the color one. So you dropped that one in favor of using all grayscale images to use the temporal one.
Yeah. So we don't use color. We use intensity images, so grayscale images, because those satellite images basically they are panchromatic anyway, so there's no color. And for the others, we have thermal. There's also intensity and for the color we just use grayscale. Yeah. And then each channel is not RGB or something like this, but kind of the video frames, and these consecutive frames. But that's not new. This was nothing we invented or so.
But that was made only for training easier, or if there are plans to do it with color as well, because I'm thinking on other kind of problems like differentiating objects depending on the color, right? So are there any plannings on that?
So at the moment, we don't have any plans to kind of generalize this to color, but one would have to think about then having let's say then there would be 3 channels, and there would be RGB from the first video frame, and then you would have the next video frame with RGB. But then in a way you have to kind of think about how you kind of define this first convolution layer. If you could just just consecutively define this as an input layer, I think one has to be careful with that, because how can you then compute spatiotemporal features, but might be possible, right? Yeah. And at the moment we are just using 2D convolution. So basically, all channels are right in the first convolution layer. All pixels of all images of the sequence are kind of are aggregated, right? One could use also groups. I mean, there are group convolutions possible. I mean, it's an implementation, or you can use a 3D convolution where you just concentrate on a certain part of the image sequence, right? But we haven't considered that at the moment.
Thank you. We have one last question from the chat from Eric K. Tokuda. Is motion perception in visual recognition also useful when the camera, as opposed to the object, is moving?
Yes, yes, of course. As I said before, in the human vision research, that this is the third option actually, and it's quite common actually, that the observer is moving and the object is moving. And that was actually the case with the satellites, because satellites are moving and the cars are moving. So basically that was the case. What we did here is we tried to eliminate the motion of the observer. So we did eliminate that by registering these video frames. So that was a pre-processing step.
Right. Okay. And then we are good. Thank you very much, Roman.
Thank you.
And thanks everybody for attending. I think we are closing. Wishing you a very pleasant evening or day. And please don't forget to take the survey on the seminar. Thank you very much.